Anyway, thank you, Jan, for those comments, and also thank you and Fetzer for inviting me to open this wonderful meeting here. I'm on home territory. This is my patch, because for 30-odd years I worked just on the next building, just across the road here. And I worked with this man, David Bohm. And I couldn't put enough photographs on the screen to show the wide range of interests that he actually had. So I've chosen just two. One of them is the, have you got a pointer on this? No? Oh, thanks. I thought there was one on here. This one? This one? Yes, okay, good. And I've got this one with a great friend of ours, Carl Prebram, who was a neurosurgeon in Stanford University, who was very interested in trying to apply quantum mechanics to the brain. And this was way back in the early 70s. So they were really pioneering this idea, and things have moved on a lot more since then. And David Bohm also was very interested in the state of mankind. I think Paavo touched on it, the communication idea. And he actually befriended the Dalai Lama and was very worried about the Middle East situation just before he died, in fact. He was almost totally worried. He thought he'd failed with his idea of communication because things were getting worse and worse as far as he could see. Okay, let me take you back, because Jan said, give us some history, give us some insight into how we linked up, what David Bohm was like to work with, and so on. Well, I'd just been finishing my PhD in the Ising model of ferromagnetism and also the protein folding problem down at King's. And there's this lovely building, which is patron is the Queen, in Great Windsor Park, where this lady, Amy Buller, this was in the late 30s, wanted to provide a safe space for unsafe discussions, which I think is a beautiful way of putting it. And to meet David Bohm there for the first time, that's very appropriate. Okay, so what was happening there was that I was trying to decide what on earth I was going to do with my life, because I was just finishing my PhD thesis topic. Hadn't written the thesis yet, but I more or less had enough to satisfy myself that all I had to do was to actually write the thesis. And there was, I was invited to this meeting by the Maxwell Society from King's College. They said, come on, Baz, come on, you've got to come down and enjoy yourself. I didn't know who this guy, David Bohm, was. It was a lovely day too. You know, we do have lovely days in London. And I thought, okay, well, I suppose I better go and try. So I sat at the back so that I could nip out quietly without disturbing people, because I'm very, I don't like listening to people, unfortunately. I like people listening to me, but not the other way around. And suddenly he started speaking. And I thought, wow, I have never experienced anything like that in my short academic life. He was asking questions that I had been asking my fellow academics at King's College, and they'd say, oh, don't worry about that, get on and do your work. Whereas David Bohm was saying, no, we've got a beautiful wine in quantum mechanics. How can we understand it? We need new concepts. And he was on about new concepts, how to bring in topology maybe, or how to bring in all sorts of things. And I thought, I'm going to work with this guy. And fortunately, there was a vacancy going at Birkbeck. He'd just been appointed the chair of theoretical physics there. And the post was actually for an experimental physicist. And I thought I had succeeded in convincing these men that I was a good experimental physicist. It was only 10 years later when they said, no, we were not fooled by that. You were the best of the bunch of theoretical physicists who could work in the laboratory. That was a nice put you down. Anyway, so David got this chair, and quite rightly, and I thought I'd go through his travels, because I think it's very interesting to know the background. He was actually a PhD student of Robert Oppenheimer, right at the stage when Los Alamos was being set up, so the Manhattan Project. And he didn't get permission. He couldn't get in there. He wanted to work with Robert Oppenheimer, but he had to stay at Berkeley, and he actually, by coincidence, joined by Sir Harry Massey from University College and Eric Burrup from University College. There was a British contingent which went across there working on unclassified issues with the Bohm. And David said to Oppenheimer, look, what am I going to do about my PhD? You're disappearing into this unknown. And he said, oh, okay. Well, I tell you what, don't bother about writing your PhD thesis, because that paper, I think, was already on the prescriptive list. We'll give you a PhD. So I think he's the only guy who's got a PhD without actually going through all the rigmarole that we've had to go through. Anyway, when the group from the UK went there, he started developing his theories of diffusion, and he actually has really laid the foundation for plasma physics. And on the strength of his work there with this group, he was invited to this. Look at the people who were in that theoretical physicists in America just after the war. There's David Bohm's just there. Can you see he's a young man? Sorry, I can't stop shaking. There's Oppenheimer looking over his shoulder, and there's Feynman just behind him. There's John Wheeler, there's Bethe, and there's von Neumann there, and there's Schwinger there. That's quite an eclectic crowd of individuals, the good and the great. So he was obviously recognized as a very talented man, even in those days. And it was John Wheeler who invited him to Princeton. And he got a 2-year contract at Princeton. And in Princeton, he continued his work with David Pines, and they applied the plasma techniques to conduction electrons in metals, and they were actually unsuccessfully nominated for the Nobel Prize. So that's the kind of standard, or it's got nothing to do with quantum mechanics, this is plasma physics. But while he was there at Princeton, he was asked to give a course on quantum mechanics. So he gave a course on quantum mechanics and decided he didn't understand a damn thing about it. So he said, what shall I do? Let's write a book. So he then wrote a book, the Quantum Theory, which was probably one of the best books of the orthodox interpretation. And in that book, he even concluded that hidden variables were not possible. But unfortunately, what happened when he was mixed up in the McCarthy business, the witch hunt. And he was arrested for contempt of court because McCarthy wanted him, being at Berkeley in the web that was around there, to testify. And David Bohm refused to testify. He wanted to plead the First Amendment, freedom of speech. But the lawyers said, no, that's a tricky one. Plead the Fifth. So he pleaded the Fifth, but they all pleaded the Fifth. And McCarthy asked the Supreme Court whether they could rule it unconstitutional to plead the Fifth in this case. Yeah, but fortunately, the Supreme Court said, no, it's perfectly all right. So he was then released. But he was banned from Princeton campus because of that. Now, in a way, this might be a good thing, because he actually befriended Albert Einstein. And they met and talked. Albert was in the Advanced Study Institute. That wasn't the Princeton campus, so they could talk with each other. And it's out of that the 52 paper, which everybody talks about now, emerged. Okay, the interesting thing was that Oppenheimer, he said Einstein offered him a job, but Oppenheimer objected. He said, please leave the country. And I've never understood why Oppenheimer said, please leave the country. Well, first of all, Bohm couldn't get a job because once you're being tarred with this kind of brush, nobody wants to know you for some reason or other. And so he then managed to go to Sao Paulo in Brazil. As soon as he arrived in Sao Paulo, the American embassy took his passport away from him. So he had to become a Brazilian citizen. That enabled him to go to the Technikon in Haifa, where he actually met Yakir for the first time. He also met his wife there for the first time. I don't know which is more important. And And then eventually, she was a lovely English lady, Sarah, and she wanted to come back to the UK, and they got Bohm got a position at Bristol University, and Yakia came across with him and did his PhD there. And this is where they published a seminal paper on the Bohm-Aronoff effect, and it confirmed beautifully a rather laboured efforts of Ehrenberg and Sidney earlier on, 10 years before, who'd actually published in a very obscure journal, in a very obscure way. But this paper that Yakia and Bohm wrote was absolutely crystal clear and brilliant. So he joined Birkbeck College. This was 65. And there's David Bohm. There's a rather young-looking fellow. I wish I was looking that young still. Interesting character was this J.D. Burnell. He was the guy who actually started up the idea that we should use X-rays to investigate biological molecules. And actually also interesting was that he was a very staunch communist who got the Order of Lenin, I think, but Mountbatten hired him for the Normandy landings. So and in fact, he actually went, the second day apparently, he went to Normandy and got on the beaches to see whether what he had predicted was correct or not. That's a scientist for you. Anyway, and then this is Ehrenberg, a lovely man he was. He actually hid in a lifeboat in Hamburg during the Nazi regime, just as Hitler got into power and came to the UK. And he actually invented the soft focus X-ray microscope, which enabled the biological molecules to actually be X-rayed. And then I want to just mention two. Jan talked about the non-locality. I want to mention two pioneers, actually. And David Butt and Alan Wilson. Alan Wilson, unfortunately, actually died in a mountaineering accident much too young. But they were the first ones to show that the EPR correlation existed over space-like separated events. And they did that they started that in the, this was not using Bell inequality aspect, and everybody else who followed was using the Bell inequality to establish that. But they were looking to see if there was any spontaneous localization, as we called it, as you pulled the detectors further and further apart. They had the world record once, which was 6 meters, and you compare with what Jan put on the screen here, it's, sorry, we were really, well, we were pioneering people. Now, you might be surprised to know that David and I hardly ever talked about the 52 paper in the first 10 years I worked with him. Okay, why? Well, David had already moved on and was against mechanism. He'd already published that. But for me, it was this opposition of all these great names. I've actually had Heisenberg actually gave me an interview. I spent an hour with him in Munich, which was very interesting. He refused to talk about the foundations of quantum mechanics. He was interested in Goldstone bosons. And I had no idea at that stage. I sort of knew something about Goldstone bosons, but I couldn't discuss anything with a guy like that about Goldstone bosons. So I managed to bullshit my way through that interview. Anyway, you see, the extraordinary criticisms that were used, called juvenile deviationism. What on earth is this? Is this science or what? And Rosenfeld, you know, said, there's no book that can save people from the confusion caused. Extraordinary atmosphere. I was brought up in, my development was in that atmosphere. And of course I kept asking, why? Is there a logical flaw? Is there something wrong with the mathematics? Was it just political? But then I found that Rosenfeld was even more left-wing than everybody thought Bohm was. So it couldn't have been that. And was it these philosophical ideas or what? And the latest one is, oh, it produces no physics, why should we worry about it? Anyway, defending Einstein, you see, he said, I'm glad, this is when Bohm was in Sao Paulo, I'm glad you're deeply immersed in seeking an objective description of the phenomena. If God had created the world, his primary worry was certainly not to make its understanding easy for us. So, okay. But still, Bohm got it too cheap in a letter to Bohm. Okay. So what were we interested in? Well, I want to tell you, Roger Penrose was with us in the maths department at Birkbeck College at the time. And we used to meet and have discussions very frequently. And Roger was interested in quantum mechanics and general relativity, and we were interested in quantum mechanics and general relativity. And one of the reasons why I got interested in the trajectories was, in general relativity, you talk about geodesics. So could those geodesics be anything with the geodesics that came out of the trajectories in the Bohm theory? Then there was and for me, the particular valuable thing that Penrose talked about was the twistor theory. And he's going to talk, I think, some Saturday, about the palatial twistor theory. He got that because he was sitting in the palace waiting for a dinner with the Queen. Yeah, okay, so what was the problem? The problem was I saw these things, which I knew was the Dirac wave function, but he also had 4 things like that, and he had symbols everywhere, and I didn't know what the structure was that he was getting it from. And it turned out he was actually getting it from Clifford algebras. And Clifford algebras have played an important role in the development of our ideas, also with David Bohm, but more with me. And from the geometric algebras there, by intersecting light rays, you can actually develop points. So you start with a space which is just made out of light rays, and you then construct the geometry points. And he had the idea of twistors because they would make fuzzy points because the twistors actually looped over each other. Okay, now one of the things that we thought was that topology might be playing an important role. Chronotopology was what David was talking about at that stage. And taking the hint from Peter Bargmann's suggestion that algebraic topology and knot theory should play a role, and also Vaughan-Jones showed that the Tower of von Neumann algebras led to knot polynomials. And I went around saying, what the hell has quantum mechanics to do with knot polynomials? So then what I thought was, well, let me look at this Clifford algebra in a different way. And we find Clifford algebras are actually stacked one on top of each other. And what you find is that the generating elements are just the things that we're using in physics, and the twistors were sitting there. They're semi-spinners in that case. But what I was interested in was the algebraic aspects of it, and then you can replace the wave function by a complex, as we know, put it inside the algebra. We put quaternions inside biquaternions. So all this stuff, which was developed by, oh yeah, so just let me make this point, that in 1964, we actually published this article, Generalizations of Twistor to Clifford Algebras as a basis for geometry, where we actually showed that this is a way to look at a geometry arising from a non-commutative algebra. Okay, so now let's go back a bit and try and say, how do we put this in? Because one of the things we're interested in here is the ontology. Now, for Bohm, the central way of his thinking was wholeness. Now, we've already seen wholeness in a way from the non-local, that occurs from the non-local. He wanted to build it in a very fundamental way. And in this sense, he was not far from Niels Bohr, although we see those words, we're not quite sure what they actually mean. David's idea was to say that if you introduce the notion of wholeness, you have to go beyond mechanism. This was the argument we were using in those days. And in fact, in his book already, the quantum theory book, before the hidden variable paper, Bohm comments that quantum mechanics shouldn't be called quantum mechanics, it should be called quantum non-mechanics, which is an interesting thing to pick up of. And therefore, when he saw the term Bohmian mechanics, he said, what on earth are they saying? Haven't they read a word of what I've said? But as it's impossible to change the word now, we have to use Bohm mechanics. But he was not happy with it. So what was Bohm trying to do? Starting with a whole, he was making distinctions, he was having relationships, make relationships of relationships, you have an order, and you have a simplicial complex. So you've got a mathematical topological idea of a discrete simplicial concept. And when I was talking about this once at the Artefini in Bristol, Science Meets the Arts, Anthony Gormley was there in the audience, and he actually seemed to be inspired by what I had to say. And we discussed things, and he eventually came up with this statue, the quantum cloud, which is actually showing how something solid appears out of out of relationships and structures of that nature, out of a simplicial complex, which I thought was quite interesting. It's still there, apparently, so if anybody wants a nice trip down the river, look out for it. Right. Now, why did Bohm not want to take the particles? Because he already knew that in relativity, there is no such thing as a rigid particle. There's just a tube of events. And these events, he wanted to say, were a process. And this is what you were saying, Jan. The whole idea is to try and get a process-developed ontology. So that becoming is basic, and being is an invariant feature of becoming. So you don't start with a particle and put them in relation. You find the relations and abstract out what the particle is from that. So you don't have to have a metaphysical idea of a particle. And here we link up very closely with Whitehead. But for Bohm, process is the concrete reality of things. And this was way back in '65, before we got on to the hidden variable papers again. So you notice no hidden variables in all of this. This was just structure, process, how do you describe it? The structure that we were finding was a non-commutative structure, and it was the structure that the early guys that you had up there were using, but then they went on to operationism because they wouldn't stay with the non-commutivity to find out what it meant geometrically or what it meant ontologically. So we have there, the idempotent becomes very special in this. And this is where Eddington comes in. The elements of existence are not hazy metaphysical elements of reality. They are represented by the idempotence, he said, of a group. I've changed it, of an algebra. So the whole thing is in the algebraic structure. That's why we've got matrices coming in. And then if you look at the idea of Feynman in his thesis, he talks about the Ket as information coming from the past, and in typical Feynman way, the Bra was information coming from the future. It's really the anticipation of a structure. And that builds in, and here you can write these things in terms of elements of the algebra, so you can be completely within the algebra, and you don't need Hilbert space in this approach. Okay, now why was I so interested in Clifford algebras? Because there was a guy at University College, I'm sorry, it's all local patch stuff, this, professor of mathematics, who was trying to generalize quaternions and biquaternions. Remember, these are things we use in quantum mechanics. And this was, have I got it there? This was 1878. But he had a process idea of physics and classical mechanics, and he had things like versors, rotors, motors, were all abstracted from this algebra. And to give you a sort of a flavor of, you have 4 points, you make lines out of them, you then find that you can turn one line into another by this quaternion, then the next quaternion, so you've got 3 square roots of -1 here, and you can actually write them in terms of the elements of the algebra, and you find this relation, and what is this relation? It's a fermion. So coming from classical physics, we've got all this stuff there already, but it's process philosophy. So the Clifford algebras emerge from movements of rotations, translations, and here we've got the Penrose picture. And I'm really putting this up for my second talk so that I can pick it up from there. Okay, then Chris Dewdney, I can't say, I know he's here because I've greeted him, came to me one day with Chris Philippides with the 52 paper. Why don't you and Bohm talk about this paper? So I said, because it's wrong. You haven't read it, have you, BJ? So I had to confess I hadn't read it. And then when I read it, I was amazed because I couldn't see anything wrong with it. And I now understood exactly why Einstein had said he got it too cheap. Because it is cheap. All you do is you write the wave function in polar form into the Schrödinger equation and have a look at the real part of the equation. and then compare it with the classical Hamilton-Jacobi theory. Now, I've chosen S deliberately here to make it look as if they're the same theory, but one is phase and the other one is action. Okay, but remember, when you generate your Feynman propagators, you always use the classical action exponentiated. So even the modern field theory uses exactly the same structure. But now we've got this rather contentious looking object, Q, quantum potential. Why? So how do you get it? You say, all right, let's assume that this momentum, this is the classical canonical momentum, assume it holds when the action becomes the phase. And then you write this equation here in a very simple form, and it's just a conservation of energy, provided you give significance to this new quality of energy, the quantum potential energy. And everybody wants to ignore it. Even Feynman, this is in his lecture notes 3, notice, some mystical quantum potential, a force which is not very big except at the junction between two superconductors, and then forgets it. The junction between two superconductors is where quantum mechanics is really taking place. Extraordinary. Okay, but now, wait a minute, wait, BJ. You're getting away with it. Momentum, local momentum. What about the uncertainty principle? Surely you can't have a local momentum. It's not possible. Well, it is, because the uncertainty principle, which I'm not objecting to, is that you cannot measure simultaneously position and momentum. Does that mean that a particle cannot have x and p simultaneously, which is what the normal view is? Or does it mean that it does have x and p simultaneously, but we simply can't measure it yet? And a lot of the opposition was that we didn't know how to measure it, but now we do. Okay? Now, what I did with the two Chris's was suggest, look, lovely PhD topics, you've got equations there, computers are just coming online, do the calculations. So we've got two-slit interference, showing the impossible being done. You're not supposed to be able to talk about which way a particle went, and you find the quantum potential is this exotic. And we almost thought, I don't know whether Chris actually did, was to patent that and put it on ties and sell it and become very rich, but I'm afraid we're not very good at that kind of stuff. And also, just to show that we also did the Bohm-Aronoff effect here, whereas the magnetic field is trapped in a solenoid here, and you find that with a given I, you've actually just shifted the fringes up, and here the quantum potential is shifted, and you see that shift in the experimental details here. And then, of course, we did the barrier, and we saw particles bouncing off long. But then, of course, it looks like interference fringes here, and those are Wiener fringes, which are well known in the optical case. So it brings out of here a lot of very interesting ideas, okay? Then we've got to seem to have a choice between what Wheeler put in his paper about the smoky dragon and the Bohm, which has the individual trajectories, but don't forget the individual trajectories are being created from a field, the phase, thinking of it as a field. So they're not quite as different. And as Jan has already said, this was non-local, and this is where John Bell came in. I saw the impossible done and his inequalities, etc., as Jan explained earlier on. Okay. So now let's look at this three momenta. Am I all right for time still, Rob? 25 minutes to go.
Sorry, 10 minutes.
10 minutes, oh, okay. Always the trouble when I start gassing. Okay, so we now have the local momentum, we now have the eigenvalue momentum, and you'll see below we have another momentum. So let's have three noteworthy mathematical results. First of all, the probability currents. We see the Bohm momentum, I'm calling this local momentum the Bohm momentum. It's just the probability current. The energy momentum tensor, if with the Schrödinger field you find that T0, which is just the momentum component of the field, is the Bohm momentum. T0 energy, and you also get, and you get another thing here. And this is another velocity, and this is what we've been calling the osmotic velocity or osmotic momentum, which comes from Ed Nelson's work. And the interesting thing I want you to note is that this goes through not just for the Schrödinger equation, it goes through for the Pauli and the Dirac equation. So it's something which stays there even in the relativistic domain. And then the weak values come along, and what we find is that the local momentum is just this, the real part of that weak value, and the osmotic momentum is just the imaginary part. Okay, and here's some lovely drawings of Bliok, who was doing it for the electromagnetic field, showing you the patterns of the different. And what you find is to get to the normal ideas of what you mean by energy and momentum, you integrate over all space. So it's a global property, and there's a very interesting paper by Colossi and Rovelli wondering about what the hell's going on, because we don't measure momentum globally, which is what you should do here. If you take this equation, we measure it locally. And then this came to my attention. This beautiful experiment, which I think Ephraim's going to talk about. And of course, if you compare it with the, you say, oh, what's this? You can actually measure these things. Hey, I've been under the illusion that it's just philosophical nonsense. And he'll go through how you do that. Now, the significant thing is here is that you couple the forward momentum, wave function forward momentum, with the polarization. And the weak stage is just a unitary transformation. It's not a measurement at that stage. It's a unitary transformation which simply changes the phase. Here's the photon coming in, you polarize it, you change the polarization, and then you measure the change in polarization. And approximately you find the weak values are in that expression, and you can get it out of measuring the number of... This is a strong measurement here, but you're measuring this phase change, and it's the phase change which encodes the information. Okay? Oh, now I've got here, brilliant experiment, but the second paper they wrote saying that they justified the Bohmian mechanics. I'm sorry, I disagree with that profoundly. The Bohmian mechanics is about a non-relativistic particle with finite rest mass, whereas photons, as we all know, are relativistic, zero rest mass particles. And what you've got to use there is the model that's based on the Maxwell's equations, and I'm afraid, sorry to point this out, that all this work already existed in the literature, which unfortunately these guys ignored. But when you go through the Maxwell field, what Rob Flack and I have shown is that it's the weak Ponting vector that gives you these are momentum flow lines and not photon trajectories as such. Okay, right, so what we've got to do in order to tell us whether this is right, we've got to use atoms. And this is what the group of us are doing at University College. And of course you need for that the spin model for the Bohmian model for spin. I'll just quickly go through that. It's easier for me, and it's just easier for you if you only knew how to make it work with Clifford algebras. You find that you get the velocity is equal to not only the Bohm velocity, but also a rotational part. So you can think of a particle having some sort of inhomogeneity. We can talk like a vector, if you like, which rotates. And I must say, and then you go to the Euler angles, and that's where Bohm, Schiller, and Thiomno, they did this, but I didn't like the fact that you have to identify this Euler angle with the phase. But if you go through the Pucker stuff, you actually can justify it without any difficulties at all. And I must point out that Chris has done a lot of work on this, which has been ignored, and I'm very angry about it. I mean, he really pioneered, and really all of this stuff, it's coming from him. Now, I want to just, how long have I got?
5 minutes.
5 minutes, okay. I just want to quickly have a look at the application to 3 magnets. Split, bring them back together again. How do you do it? Well, if you do the Bohm theory and you only put 2 magnets in, you find the trajectories actually bounce like that. If you look at the spin, you find something very interesting going on here. Look, the spin vectors actually change direction. And this is outside the magnet. It's nothing to do with the magnet. It's outside the magnet, and it's the quantum torque that is working. There's the quantum potential is actually active there. And then if you put the next magnet in, and I thank Robert for these calculations, you actually combine it back together again. So why am I doing this? Because we're told by this Engert, Scully, Sussman, and Walter that the Bohm trajectory here is macroscopically at variance with the actual observed track. Tersely, Bohm trajectories are not realist. They're surrealist. Sorry, mate, you got your physics wrong. Right, how? Well, this is what they're saying standard quantum is with quantum mechanics is. And if you look at that, they preserve the spin right the way through that interaction region. Okay. First of all, my first worry was, what are they talking about? Trajectory in standard quantum mechanics. Because we've got Landau and Lifshitz saying, there is no such concept. But then later on, he says, yeah, but what we can do is we can take a region and we can say the particle is, and provided delta V is large enough, we don't get into trouble with uncertainty principles. And we find the particle eventually here. How did it get there? The probability current. Okay? And then what these guys show is the probability current for the symmetry of this case, it's 0 across that central reservation. And yet they've got the damn things drawn going across the central reservation. And in fact, if you polish it up a bit more and use the conservation of probability, what that tells you, that if you've got a particle in the top half here, that you make a contour out of that, if you keep it in the top, you'll never find the particle in the bottom part. Okay. And then finally, we are now in a position to settle this experimentally. Because we've now got these changing with the weak values. We can measure these angles using the weak values. And that is what we're now, one of the proposals we're doing. And here is a list of experiments that we're actually contemplating doing or in the middle of doing. So we've got there the weak value spin for helium. We've got the local momentum using both helium and argon, perhaps. We measure we can actually try to measure the osmotic momentum to see whether it has numbers we can put to it. We can construct the two-slit interference and momentum flow lines, settle the dispute, and extend the ideas and, of this to apply to gravitational AB effect. And here's the team. Please address all questions of experimental nature to these guys, because the answer you'll get from me, I wouldn't trust. And I also just like to thank Robert and Peter, and Dennis and Lyndon for their help in all of this, and a very special thanks to the Fetzer Foundation.